Okay, good afternoon, everyone. Welcome to our Renaissance webinar series number 2, Storage, the Holy Grail of Energy Transition. And in this webinar, you will learn about how Sunamp's thermal storage contributes to renewable energy transition, system optimization, and decarbonisation of DUTH University campus in Kimmeria. Okay, firstly, let me quickly introduce Renaissance project. So Renaissance stands for Renewable Integration and Sustainability in Energy Communities. And Renaissance will deliver a community-driven, scalable, and replicable approach to implement new business models and technologies to supporting clean production and shared distribution of energy in local communities. And here are our partners in this project. And today is mainly presented by DUTH and Sunamp. And the deep blue is helping with the webinar organization. Okay, here's today's agenda. We will start with introduction by Rebecca, and then followed by Professor Bossari's speech talking about storage, and then followed by myself, Tianyue Li's speech about the science of PCM. And then Dr. Maurizio Anzaglio will talk about Sunamp and the applications of thermal storage and in Kimmeria pilot site. And finally, we will have our question Q&A session. So during the webinar, as Rebecca just now mentioned, that we will have our recording all the time. So at certain time, we might ask you to turn on your webcam to participate into certain events. And if you have any questions, you can also leave your questions or comments in our live chatting function in this webinar. Okay, firstly, let's welcome Rebecca Whiting talking about project introduction and first results. I will hand the screen sharing to Rebecca. Oops.
Thank you very much, Tianyue.
Thank you.
I will share my screen. Yes, you should be already able to see my screen. Oops, not this one. Can you see my screen now?
Not yet.
No.
Oh, not yet. So just give me. Yes. Now you should see my screen.
Tianyue, can you mute your mic, please? Don't speak. There is some noise. Thank you.
Okay. Can you see my screen now? Okay.
Yes.
Yeah, okay. Great. Thanks. Because I don't see you anymore. I just see one person at a time. Okay. So the project Renaissance is mainly about the deployment of renewable energy communities.
Rebecca,
Yes.
I suggest to close our cameras if we are not presenters, like the bandwidth. Thank you.
Yes. Okay, so I will keep my camera on then, and hope you will shut your cameras down. And then for the question and answer session, we will be very happy to see each other's faces then. Well, the Renaissance project is mainly about the renewable energy communities, following the directive that has been open to all European countries in 2019. Now the transposition of the law is almost finalized in all European countries, but of course with this project we try to support the deployment, offering an integrated approach towards their full deployment and supporting especially citizen communities in the implementation process. So we imagined to help them find consumer-centric solutions and offer interoperable tools towards the full deployment, not only of technologies, but also of decision-making processes. So what we did was to find ways and processes to link together an analysis phase in which we involved stakeholders in a MAMCA approach, a methodology which is the multi-actor, multi-criteria approach, helping stakeholders find consensus around a specific energy scenario or energy layout. Then what we have also designed is the Reenergize tool. It's an optimization tool which can calculate in a very preliminary way the energy system layouts that are most suitable for that specific situation and condition, and make some comparisons between the options that specific energy community has to optimize the use of the consumption and production of energy, especially when you talk about renewable energy that comes from different sources, and we will see it in the Kimmeria pilot site now. Then we went through all the phases of this process in our 4 European pilot sites, and I will show you the different pilot sites. But then at the end, we offer also a grid management tool, which is the Renaissance platform that has still to be delivered, but it's almost there. You will see it after the summer. That helps the management, the daily monitoring and management of the specific energy community. So we offer tools for each phase: the design phase, the implementation phase, in which you have to set up your energy community, and the operation phase. This is basically what the project does. We tested our tools in 4 European pilot sites: in Emnes in the Netherlands, in the student community campus in Kimmeria in Greece, which we will go into much more deeper detail today, the university campus hospital in Belgium, in Jette, also linked with the student campus, and in a ski resort in Galicia in Spain. You can find more information about all the project and all the pilot sites on our YouTube playlist, which I was trying to show to you. We have more than 17 videos recorded with interviews to users, with recordings from the different pilot sites, and you can see here that we have been visiting all the different pilot sites just exactly with the objective not only for us to follow the implementation process, but also to let our followers know what actually happened in each pilot site and which were the challenges, both in terms of stakeholder engagement, community building, but also the technical issues that have emerged. I'm very happy today to let Sunamp and DUTH talk about their cooperation on the Kimmeria pilot site and tell us what happened with this innovative thermal storage unit that has been installed in the Kimmeria pilot site. So my presentation is over, and I leave the floor to Professor Pantelis now. Professor Botsaris, Pantelis Botsaris. Please.
Okay, Rebecca, thank you. Yes, my surname is Botsaris. Pantelis is the nickname, okay? I will try to share my screen now, and I will try to do it right now. One moment. Okay. And you see my screen?
Yes, we do.
Okay, I will be in the display mode. I think I'm ready. Yes. Okay. Now, good morning and hello everybody. My name is Pantelis Botsaris and I am professor at Democritus University of Greece in the Department of Production Engineering and Management and Head of Mechanical Design Lab. I'm very glad to be here with you today and thank you for your participating in this event. The next few minutes. I'm going to give you a brief and I hope comprehensive description of some terms like storage, like techniques of storage energy, etc. of my presentation with a central theme of thermal energy storage. Okay, you see the next slide? Okay, thank you.
Yes, we do. Not in presentation mode, though.
Not in presentation mode. Yes, I have tried to be at presentation mode, but I don't know what happens and I can't.
Okay, just simply follow as you are doing now. We will try to read it.
I was going to talk about and give some details about our university and my lab, but unfortunately, due to all the delays, I will pass these slides because we have to keep the time. So, okay, I'm going to talk about the energy models, the new energy models that we will have in Europe till 2050. The energy transition is a pathway toward transformation of the global energy sector from fossil-based to zero carbon by the second half of the century. At its heart is the need to reduce energy related to CO2 emissions to limit climate change. Decarbonisation of the energy sector requires urgent action on a global scale, of course. And while the global energy transition is underway, further action is needed to reduce carbon emissions and mitigate the effects of climate change. Renewable energy and energy efficiency measures can potentially achieve around 9% of the required carbon reductions. Flexibility has become a common byword for the energy transition. While everyone agrees that we need more flexibility in pure power energy systems, views vary widely on how to achieve this, particularly to improve grid integration and make maximum use of solar or wind or ocean potential. To transfer our energy system towards one dominated by renewable energy, flexibility has to be hastened in all parts of the power system. Power system flexibility spans from more flexible generation to stronger transmission and distribution system, more storage and more flexible demand. Production of heat and cooling and synthetic gas like hydrogen for renewable electricity is also key for energy system decarbonization in the long term, and once in place it can be a significant additional source of flexibility for a power system. And of course, in the center of all of this, energy storage plays a key role in this transition. District heating and cooling, together with thermal energy storage, are potential technologies for the integration of renewable energy and the reduction of CO2 emissions in the European energy sector, and the interaction and development between both technologies is of significant importance. District heating and test, together with, for example, hybrid systems or heat pumps or organic grinding cycles engines, are identified as cross-cutting technologies by the Renewable Heating and Cooling Platform, meaning that are key enabling technologies for fully decarbonizing the heating and cooling sector by 2050. This can maximize the benefits that district heating provides to the energy system. One of the major challenges for future energy system is to overcome the mismatch between supply and demand caused by the increasingly strong deployment of intermittent renewable energy sources. By interlinking the electricity sectors and the heating and cooling sectors, and by deploying thermal storage, the mismatch and their maintenance problems can be addressed. These new operational constraints in future energy systems also require the development and deployment of energy management tools in both electrical and thermal networks. This intelligent management is achieved with new information and communication technologies and new smart energy system approach. The way TESS contributes to solving the mismatch between supply and demand is by providing management capabilities to the system. Now, an energy storage system can be described in terms of the following characteristics, like capacity, power, efficiency, storage, cost, or charge and discharge time. For example, storage period defines how long the energy is stored and lasts hours to months, hours, days, weeks, months for seasonal storage. District heating can be seen as a thermal distribution network of pipes filled with a heat transfer fluid, which is often water. In this network, mass flow is being controlled by pumps, valves, etc., while extraction or supply of heat and cooling is maintained by the use of so-called agents. Agents use heat exchangers to extract or supply heat to the system. These agents can be divided in three main pillars or categories: the consumers, the plants, and finally the storage. For example, plants, the supply side, the main task of the plant is to balance energy flows, often responsible for the supply of heat in the system. A plant has no demand itself, but equalizes the energy balance of the network. The evolution of the district heating can be categorized in different generations. For example, in this figure, or the figure in this slide, shows an illustration of the evolution of these generations. For example, the first commercial district heating was produced in the United States around 1880. This commenced the first generation of district heating, which used steam as a heat carrier, or since 2014, a shift is occurring in which the fourth generation of district heating is being applied. This generation is characterized by its search for sustainable heat sources and smart thermal grid, and water is still used as they kept around 65 degrees Celsius to minimize the grid losses. Now, there are various forms of energies, and their storage methods and mechanisms have been described, as we can see in this slide. But then we will focus from now on storing thermal energy. The importance of a test system in future energy systems with high amounts of independent renewable energy sources is due to the fact that half of the total final energy consumption worldwide can be attributed to heat. Thermal energy storage is much cheaper than electricity storage, and it has high potential of integrating independent renewable energies such as wind, solar, ocean into the heating and cooling sector via heat pumps, electric boilers, etc. TESS provides several benefits to heating and cooling networks, including reducing peak thermal demands, increasing the efficiency of the system, and integrating other heat sources as industrial, waste heat, or seawater. The application of thermal energy storage with renewable energy sources, waste heat, or surplus energy production can replace heat or cold generation from fossil fuels, reducing greenhouse gas emissions and reducing the need for thermal power capacity of the generators. It has estimated that in Europe, around 1.4 million gigawatt hours per year could be saved, and 400 million tons of CO2 emissions avoided in the building and industrial general sectors by more extensive use of heat and cold storage. Thermal energy can be stored as a change in internal energy of a material as sensible heat, latent heat, or thermochemical, or combination of these. When we talk about sensible heat, storage is due to temperature change of material, while latent heat storage is due to the phase transformation, either it is solid liquid, liquid gas, or solid solid. Of course, different types of thermal energy storage is shown in this slide. One comment, the third mechanism, chemical reaction or sorption process takes place on the surface of the material. In all cases, heat can be either absorbed or released from the material. In this slide, we see a classification of the methods and techniques used for the storage of thermal energy as a function of the energy density of the storage medium used and the technological maturity of the method. Another classification of thermal energy storage system can be based on the storage time, the length of the time the energy is stored, and we can find here short-term storage systems or mid-term storage for solar supported district heatings or long-term storage for solar space heatings, or we can see central solar heating plants with seasonal storage. In this slide, we observe a classification of test methods based on their TRL index, technological readiness level index. The higher the value of this indicator, the higher the technological maturity of the respective method is considered. The basic principle, of course, for the all-day methods is the same. In all the test application, energy is applied to the storage system for removal and use at a later time. What mainly varies in the scale of the storage is the scale of the storage and the storage method used. The process of storing thermal energy can be described in three basic steps referred to as a cycle. These steps are charging, storing, and discharging. The storage cycle applies to sensible, latent, and of course, chemical storage. Capacity, power, and discharge time are interdependent variables. In some storage systems, capacity and power can also depend on each other. Typical parameters for test systems are shown in this table, in this slide, including capacity, power, efficiency, storage, period, and cost. High energy storage density and high power capacity for charging and discharging are desirable properties of any storage system. Of course, for example, in this table, we should not miss the fact that where quantitative data related to materials or technologies are mentioned, we run the risk of making mistakes, not use very updated values at the space of the modern technology and, of course, the current competition. Here, the lower figures.
Sorry, but now I think the quality is very too bad to hear everything you say. I don't know how we can improve this.
Sorry.
Yeah, the quality in the last slide was quite bad. We could barely understand what you said.
You talk about this one or this one?
The previous one, the one with this one, but now it's much better. So maybe if you stay a little closer to the microphone, it's clearer for everybody.
Okay,
if it's possible for you. Thank you.
Thank you, Mauricio, for your remark. Thank you. I will try to keep as close to the microphone as I can. Now, the lower figure in this slide, as already said, shows an example of a 24-hour operation of a test system with charging, storing, and discharging phases, enables a steam turbine generator to extend electricity production after sunset, providing valuable firm power during peak and demand periods. Tests can also be classified into decentralized and centralized systems. For example, centralized energy storage can be found in district heating and cooling networks, large industrial plants, combined heat and power plants, and renewable energy plants, or while the decentralized tests are found commonly in domestic and commercial buildings. Now, what are the main features for the selection of thermal energy storage technology? the large storage capacity, the existence of storage medium with the appropriate properties, maintaining a uniform temperature, its capability for high storage efficiency, durability and zero losses in performance and storage capacity, high charging and discharging speed, negligible heat losses in the environment, low risk, low cost, long life duration, and of course, resistance to the corrosion phenomena. Now, sensible heat storage materials or sensible heat system is the simplest method based on storing thermal energy. Sorry, one moment. I have to close my mobile. Sensible heat storage system is the simplest method based on storing thermal energy by heating or cooling a liquid or solid storage medium, water, sand, molten salts, rocks, concrete, etc., with water being the cheapest option. The most popular and commercial heat storage medium, of course, the water, which has a number of residential and industrial applications. Underground storage of sensible heat in both liquid and solid media is also used for typically large-scale applications. Sensible heat storage has two main advantages. It's cheap and without the risk associated with the use of toxic materials. The sensible heat systems utilizes the heat capacity and the change in temperature of the storage medium during the process of charging and discharging phase. The amount of heat stored depends on the specific heat of the medium, the temperature change, and of course the amount of storage material. The table here shows the most used sensible heat materials and their properties. Water appears one more time to be the best sensible heat material or liquid available because it is inexpensive and has a high specific heat. However, above 100 degrees, oils, molten salts, and liquid metals are used. For a heating application like rock or concrete, storage materials are used. On the other side, latent heat system materials, also known as PCMs, due to their property of releasing or absorbing energy with a change in physical state. The energy storage density increases and hence the volume is reduced in the case of these materials. The heat is mainly stored in the phase change process at a quite constant temperature, and it is directly connected to the latent heat of the substance. The use of a such system using PCMs is an effective way of storing thermal energy, has the advantages of high energy storage density and the isothermal nature of the storage process. The main advantage of using latent heat materials over sensible heat materials is their capacity of storing heat at almost similar temperature range. Initially, these materials act like the sensible heat materials, in that the temperature rises linearly with the system enthalpy. However, later heat is absorbed or released at almost constant temperature with a change in physical states. Latent heat system materials are broadly classified based on their physical transformation for heat absorbing and desorbing capabilities. As we can see from the slide, were classifications of solid to liquid PCMs, which are further classified into organic, inorganic, and eutectic materials are presented. When we talk about eutectic materials, are a combination of two or more low melting materials with similar melting and freezing points. PCMs are classified as different groups depending on the material nature: paraffins, fatty acids, salt hydrates, etc. Another feature found in phase change materials is the containment. Containment of PCMs helps contain the material in liquid and solid phases to prevent its possible variation in chemical composition by interactions with its surroundings, to increase its compatibility with other materials in the storage system, to increase its handiness, and to provide a suitable surface for heat transfer. Types of containment studied are, for example, the bulk storage in tank heat exchangers, macro or micro encapsulation. For example, and so, as shown in this slide, the containment can be used in one tank test system. The heat is transferred to or from a space between to or from a heat transfer fluid as the heat transfer fluid flows through the space between the capsules. During the charging mode, the hot fluid from the solar, for example, field is circulated through the tank. The PCM inside the capsules absorbs latent heat and melts. During the discharging mode, cooler heat transfer fluid is circulated through the tank to absorb heat from the PCM, causing the encapsulated PCM to freeze. The heated fluid is then used to heat the power block, working fluid through a heat exchanger. A current example of the use of the phase change materials is from the field of construction use. PCMs are considered to be potential energy-saving materials due to latent heat absorption. They can substantially increase the thermal mass of buildings compared to conventional materials as presented in this figure. At this point, I would like to take this opportunity to note that this method of storing energy with PCMs was also tested in our pilot site during the Renaissance project, and of course, which will be described in more detail by our next speakers. Now, potential barriers for test systems. Very soon, market entry and costs, material properties and stabilities, in particular for thermochemical storage systems, TCM systems, specific design, I talk about air conditions and the requirements that all we need, and research and development activities focus on all test technologies. Finally, we talk about more complex systems that require everyday efforts to improve reacting materials, as well as a better understanding of system integration and process parameters. Now, a few words about our pilot site and our role in the Renaissance program. Our pilot site is located inside the university campus near Xanthi, North Greece, and includes a small district heating and cooling system that cover the energy demands of 11 buildings of approximately around 15,000 square meters. It includes 8 buildings for students' residencies, and 1 energy hub, 1 restaurant, and 1 amphitheater, all owned by our university, the Democratic University of Thrace. Students' residencies are provided free of charge to youth students with the main criteria to the family income. We talk about a kind of social housing. The district heating and cooling system is powered by a hybrid system of a total power of 2.5 megawatts hour thermal energy by a gas boiler and a solar thermal energy system of approximately around 2,000 square meter net aperture area. The hybrid system has a thermal energy storage system that consists of 4 tanks of 10 cubic meters each of hot water and an absorption chiller for cooling production. Besides the hybrid system, the pilot site also includes a geothermal heat pump system, a PV system with battery storage, and a small vertical axis wind turbine. In this slide, we can see the existing equipment of our pilot site and equipment acquired during the Renaissance program, like the 2 PCMs thermal batteries from the Sunamp or an ORC turbine engine, smart meters, etc. The main scope or the aim of our pilot is to explore, leverage, and mobilize the university to apply or try to apply schemes for a social group like students in order to participate in the operation and management of a local renewable energy community, gaining benefits that are not only necessarily financial. Some experience and remarks that we have also already taken from this project. A test can help to balance energy demand and supply. As we found through the assessment of appropriate performance indicators, a test can also reduce peak demand, energy consumption, CO2 emissions and costs. A test is used in many applications, like the store of heat, to couple waste heat and district heating systems, or to couple ORC engine and combined heat, etc. And by interlinking the electricity sectors and the heating and cooling sectors, and by deploying thermal storage, the mismatch and intermittence problems can be addressed. As a final remark that we have learned during this project, the path of energy transition, in addition to technological means, requires more than anything else human participation. Human participation requires constant information, education, and awareness. I think that I am on my time, and I will be here with pleasure to answer if you have any questions. Thank you very much.
Thank you, Professor Botsaris, for your amazing speech and very thorough explanation on the TES, thermal energy storage, and also for the Kimmeria pilot site. We will leave the question and answer session at the end of our webinar, and we will move on to our next speech. So just give me a second to share my screen. Our next speech is presented by myself. Hi, everyone. I'm Tianyue Li. I work for Sunamp Limited, and I'm a business development manager. And I'm also the project manager for the Renaissance project on behalf of Sunamp. So in my presentation, I will talk about PCM also, and because Professor Botsaris talked about the whole picture about the thermal energy storage, and he also mentioned PCM is a very crucial part of it, which has also been applied to our pilot site. And I will talk about how it works and also some advances that has been developed by Sunamp. Okay, so first we come to the very first question, beginning question, is that why renewable energy is a must for the future? So why we have to switch to renewable energies from the traditional kind of fossil fuel energies? Because as we all know, the climate change is getting more and more severe and causing the fuel poverties, and also people are struggling to get sustainable energy resources for life, for living, for production, every field of life. And also, especially after recent war between Ukraine and Russia, as we all know, the energy prices has been increasing dramatically. However, if we have switched to renewable energies, which are mostly free, clean, and endless, it will be beneficial for the whole society. So renewable energies, they need to be stored to be utilized. Why is that? Because when we are thinking about the wind energy, solar energy, these type of energies, they are free, they are from the nature. However, they are intermittent. What intermittent means that when we need them, they might not be generating. For example, when we're living in the house and we come back from work in the evening, we need electricity. And during the evening, there's no sunlight to generate electricity. So we have to store those energy during the daytime that has been generated by the solar PV, and to use them during the time that there's no sun. So same applies to other sorts of renewables. Most of them are intermittent. By having a storage system allows us to fully utilize the renewable energies whenever and wherever we want. Here is an illustration picture of how the storage unit can be combined in multiple types of renewable energy sources, including solar PV. PVT means with the solar thermal or combined with solar PV and thermal. And also here is we call it air source, or the heat pump that's generates the captures the heat and magnifies the heat from the air. So this part is mainly talking about heat, thermal energy, and also like other source of heat like boilers, CHP, etc. Even from the grid to shift the peak can also be realized by having storage and to provide, in our case, is cooling, heating, and hot water if it is stored in the way of thermal energy. Here is what we're gonna talk about more. Why thermal energy? Next slide. Yeah. So why we talk about so much about thermal energy? Because we all know electricity is also a very important type of energy. From this pie graph, you can clearly see that thermal energy takes almost a half of the total energy consumption worldwide, which is almost 2.5 times more than the electricity consumption. And if we focus on our lives, day-to-day lives, and also like students' accommodation, etc., these kind of residential places, we can see that actually almost 80% of energy is consisted by thermal energy. Here it's space heating and cooling, 40%, hot water heating, 23%. We include cooking, which is also heat, 5%, and fridges for cooling is also 8%. So all of these, it's a very huge amount of energy that is consumed in the way of thermal energy. And compared to electricity energies, we know that thermal energy plays a very key role in our daily life. So what we use to store thermal energy? Here, as it says, it's phase change material. In Sunamp, we developed the phase change material with different temperatures, phase change temperatures to store the latent heat, which has been explained by Professor Botteris earlier, in order to have high energy density thermal energy storage. So here is a video that shows you how does the phase change process happens. Okay, so phase means that it turns from solid to liquid. So these are two phases. Change means it's interchanging, and during this process, the latent heat is released. So as you can see, it's solidifying. So it's changing from solid to liquid. And this is like a pocket-sized hand warmer with a PCM gel inside. And during this process, you can feel that a huge amount of heat is generated. You can feel it's getting really warm in your hand. And that warmth can last for a while. So differently from like a hot water bag, which will get cooled very soon, using PCM can have much higher energy capacity in this case. So we utilize this phase change material into our thermal storage applications. However, there are many problems associated with PCMs. Here is a list of them. For example, corrosion. What does it corrode? Professor Botteris said there has to be a heat changer inside to extract the heat. So corrosion on heat changer is a big problem for long-term usage. And then low thermal conductivity, flammability, especially for organic PCM, they are wax, they are like flammable, dangerous, low cost, and incongruent melting, which means that it doesn't go back to liquid and solid. It will just stay at one phase, which means that it will be dead. And finally, long life cycles, so that it can be repeated and cycled for tens of thousands of times in our case. Yeah. So here, I'm not going to detail, but here we see like from solids to liquid phase, there's a melting process which produces the latent heat, which is a majority of the thermal energy from the PCM. Yeah, and this is a reversible process, and we want this cycle to happen for as many as possible. So in Sunamp, after many years development with the University of Edinburgh, we have developed our plantigrade phase change technology. Plantigrade, it means that it has a very long life cycle and very high stability for the PCM. And we have already certified our PCM with raw PCM certification, and we got the grade A, which is the highest grade for cycle stabilities, which is like 10,000 cycles. But in our lab, we have done more than 46,000 cycles with under 10% of performance drop. And so it's very phenomenal to see that our PCM is very stable, and that is a core to sustain like long life use in the thermal energy storage. So yeah, so this is the core of our technology. And in the following presentation, we will welcome Dr. Maurizio Zaglio, our Global Head of Partnership at Sunamp Limited, to talk about how we apply this technology into applications, and how does our unit work in a Kimmeria pilot site. So let's welcome Maurizio.
Thank you very much, Tianhui, and thank you for the first part of the presentation introducing our technology. We can move to the next slide. So we focus a lot in the conversation about Professor Bozzaris and for Dr. Lee about introducing the thermal storage technologies and the PCM based thermal storage technologies. And in these next few slides, I will try to present you how Sunamp has achieved commercial stage with a product based on phase change material, and I will present some case studies, so real life systems that are used every day and that are sitting in people's homes. Let me start by saying, once more, how we use PCM in our technology, in our products. So we have a core, an internal cell that includes a very powerful metal heat exchanger that is immersed in our proprietary phase change material. And this internal enclosure is then very well insulated. We use vacuum insulation panels to minimize the heat losses from our storage, and then it is protected by an external metal shell. Professor Bozzaris showed a very interesting slide with the requirements that that a good thermal storage technology should meet. It was a list of properties, and I believe, I'm actually sure that our product is ticking all the boxes on that list. So I am very pleased to be able today to present this to all of you. The main evident advantage of our product compared to the incumbent technology, water-based thermal storage, is evident in this picture, which is a real picture taken from our experience room in our factory. As you can see, our box, so the product on the right, is much smaller than the water tank on the left, and these two products are able to store the same amount of energy and therefore to provide to the final user, to the house, the same amount of hot water. And I think we can all appreciate the space savings of a PCM-based technology compared to a sensible heat technology. As I also already mentioned, the heat losses are extremely low, and this results in an efficient product over time. And there is very low water into our product, and this is something people not immediately think about, but this solves many issues. For example, we don't need anti-Legionella cycles in our product. And because of our very well designed internal metal heat exchanger, we can exchange high thermal powers with the heat transfer fluid into the heat exchanger, between the heat transfer fluid, usually water, and the PCM, and therefore we can provide high flow rates of water to the building. Can you go to the next slide, please, Tianwei? And we have been able to develop over the years products at different scales. And in fact, we are present in both the residential market, and in the previous picture, and also over my shoulders, you can see some examples of our standard products for that application. But we also are active at larger scale, where we can apply our heat batteries to large buildings or district heating networks that were also mentioned during the presentation of Professor Botharis, as well as commercial building and industrial buildings. And we have been able to maintain all the main properties that I've just explained in the previous slide, also while scaling up the size of our heat batteries. And can you please proceed to the next slide? This is the first example of a very successful project that we have run in the UK. I would like to mention that this is a fully commercial project, and therefore our technology has been chosen purely based on the advantages that it brought to the final users and to the and all the stakeholders involved. In this case, we had, with our partners that you see on this slide, replaced 364 gas combination boilers that were into each apartment of multiple tower blocks. And these customer wanted to get rid of gas from all these buildings, and therefore it has decided to replace this with heat pumps. Heat pumps was the preferred technology. Of course, the big issues of working with heat pumps is they require large water tanks. If you have a heat pump at your home, or if you have seen heat pumps around you, you will notice that they are pretty compact and usually sitting outside, but they always come with a big water tank to cover the hot water service of the house. Because these apartments were designed to host a very compact instantaneous gas combination boilers, it was extremely difficult to install heat pumps with the water tanks that usually comes with that for the hot water. And in this case, therefore, Sunamp was chosen to really unlock the project. And in particular, we have been able to take a minimum space into the apartment to achieve what the customers wanted to achieve. A heat pump that takes heat from a shared geothermal loop that is shared between all the apartments, upgrade the temperature of this water to what is required for space heating and for recharging our technology, our product, and then the Sunamp heat battery provides hot water to the whole house. Next, please. We also have experience with air to water heat pumps. This is an example, a real installation with a Daikin heat pump. And again, on the right, you can appreciate that even in this case, there wouldn't be no space actually to install a traditional water-based boiler to be recharged by the heat pump to provide hot water to the house. But by using our technology, we've been able, to fit in this limited space enough capacity, storage capacity, to serve the water requirements from this family. Please, next one. And of course, as has been mentioned before, storage is a key component to maximize the self-consumption of renewables in the residential, in the building space. And this is an example of a project where we have linked PV panels on the roof of this house to a Valent heat pump by using a device, a power diverter from My Energy Eddy, from My Energy, a partner company, that basically senses how much electricity is exported at any time by this building and diverts the excess electricity to our product to warm up the phase change material and then to store it to provide hot water on demand. And the Valent on the side is also working to increase the efficiency of the system and to provide the space heating to the house and to recharge us when not much solar is available in the building. Please. And this is the second last slide of my presentation, just to tell you that actually phase change material storage is at an advanced commercial stage, so we shouldn't look at it only as an R&D system, but Sunamp has been able to commercialize this unit, and we are growing rapidly globally because, of course, our aim is to substitute any water tank out there with our phase change material-based technology. Please. And Professor Botzaris actually explained this slide much better than me. So I will just probably reiterate again the importance of storage, any kind of storage, but I hope I was able to convince you about the benefit, commercial benefit of phase change material-based storage. But let me highlight the importance of storage in a site like this that combines multiple different sources of renewable energy. If you can imagine, these are not constant, are variable, not easy to predict in many times. You know, just a cloud over that solar field can change the output from the solar panels. And therefore, that's why storage is hugely important to maximize the penetration of renewables in any building, and especially in sites like this that serve hundreds of people, if not thousands of people at the same time, and to match or to decouple generation from consumption, and therefore really contribute to clean the energy system in the building sector. I believe this was my last slide, Tianwei. So
Yes.
thank you very much for your attention. You can find many more information on our webpage, including the case studies that I have just described and more. And feel free to contact us at any time if you would like more information. Thank you very much.
Thank you, Dr. Maurizio Zaglio, for the detailed explanation on how PCM has been utilized in real case applications and in DUTH pilot site. So hope this gave you all a very clear idea about the thermal storage benefits has been brought about to our day-to-day life and to the world and to the utilization of renewable energies. So now comes to our Q&A session. We have around 10 minutes to have the Q&A. So everyone is welcome. If you want to give a question, you can either write in the group chat or just turn on your mic and talk to us, and we will be here to answer your questions. Thank you.
We don't bite. Don't be shy. Don't be shy.
Okay, let's start the cycle of the questions. I have a question for Dr. Zarglio. May I?
Please.
Yes, it's undoubtable that the batteries that you presented are of high energy density. Have we had an estimation about the cost for a common house holding about a thermal battery around 60 kilowatt hours? What's the cost compared to a common electric boiler?
60 kilowatt hours is not a standard product for us, but I can keep this answer quite a high level, and then we can continue the discussion offline, and I can provide exact prices for our standard products. But I would like to say that we are already today competitive to water-based storage. I have presented case studies that were based on commercial projects where we have been selected not only for the space saving.
It was amazing. Yes, you are right. It was amazing.
So we are competitive. Of course, we provide many benefits, so we price ourselves a little higher water-based storage. But I will be able to share with you our, let's say, manufacturer recommended retail prices for our standard products, and we can continue this discussion more than that.
Thank you. Thank you.
Anyone else has any questions?
I have a question which might sound a bit silly, but since I'm no expert in energy, I still would like, because I was curious also when we visited the Kimmeria pilot site, if the thermal storage unit that you have installed, is it able to, I mean, I imagine that of course you can add up other units to store the thermal energy from all the different sources, but is it something that you can choose or decide if you want to use them like all together? If you want, let's say, to install 10 units, can you, without making any hardware change, is there a way for the customer to manage if they want to, let's say, store all the energy distributed in all 10 units, or maybe in another situation 6 months later decide that each unit is dedicated to a specific source? So I want the solar panels to go to the unit 1, the thermal, the waste energy go to the unit 2, and so on. Can this be done without making hardware changes, but only a software managing such thing, or is it something not yet possible?
Very good question. So our standard product can have 1 or 2 circuits into the heat battery, meaning that at any given time, 1 unit, if we select that with 2 circuits, can be connected to 2 different sources, for example, and the discharge would also share one of these loops when the heat is needed. Or one source is used for charging and the other loop is only used for discharging. When you have multiple modules together, it becomes extremely flexible. So as you are asking, by designing the system around our modules, it will be possible based on different input, which can be time of the day or availability of renewable energy or the month, you know, whether it's summer or winter. It will be possible to select specific modules that can therefore operate at certain times and under certain conditions. So what you're asking is true. Our technology is very flexible, and especially when you have multiple modules together, by designing the system around it with sensors, valves, pumps, usually and of course a well-designed intelligence, which is also the main topic of this project. What you're asking is achievable, absolutely, and it can become extremely efficient as well.
Yeah, so that means that for an energy community, which is what we imagine in the future, you can set, I mean, optimizing year by year your system. If you have a lot of battery units, be it storage, thermal storage, or other kinds of storage, you can definitely, let's say, set up the algorithms that manage the different way of how energy produced and consumed is managed by the best systems. And through the years, it gets better and better, if I'm not wrong. I mean, I imagine that the more experienced the system and yourself you get, the better it will manage energy. Okay.
Absolutely, and this is also one of the main reasons for us to become partner of this project, to start looking at these topics.
Yes, for me it was a very huge lesson to learn, because even if I have a very small knowledge about energy and storage, I thought that we did not have, I mean, we have a lot of mature systems, but I thought that there were physical limits or physical constraints that did not really allow to manage with such a flexibility battery systems, especially when you had to mix many different sources of energy all together. So this is a very big lesson learned from me. That I'm no energy expert, but this is nice to know now. I can tell people when they ask to me that it's something that can be done. Thank you.
Great.
Thank you, Rebecca, for the question. So if you don't have further questions, or if you might have questions in later stage, you are always welcome to contact Professor Botaris or contact me or Maurizio. I believe that we have our email address. I put mine here earlier. Sorry, yeah. So you can reach us. You can also come to visit our website, sunw.sunamp.com, to learn more about our technology and applications regarding PCM. So thank you very much for your attention, and I hope you had learned a lot from this webinar. And yeah, thank you.
Thank you for the organization, and goodbye, everybody.
Thank you, Tianli. Thank you, everybody. Have a nice day, everyone.
Thank you, Professor Botaris, and thank you, Rebecca, for the organization.
Thank you, everyone, and see you in the next edition of the webinars. Thank you. Have a nice day. Goodbye.
Thank you. Bye-bye.
Thanks.
Goodbye.
Bye, Bola.